All right, so I have our springy box and then another box. And we're going to pretend that they're connected by an ideal string. So we're going to need to talk about that. But I don't have a string, so you just have to pretend. I'm going to pull on the lead box with my 50 newtons, and both boxes are going to accelerate to the right across the table. So that's our situation, okay? So we got our, two boxes on the table connected by an ideal spring. So I'll call them box 1 and 2. So we'll have box 1 was our 10 kilogram springy box. And I said that the coefficient of kinetic friction between that box and the table was the 0.15. And then we're going to have my second box, which was smaller, so I'll make it 5 kilograms instead. And since it's made out of different stuff, it could have a different coefficient of kinetic friction. Let's say it's, I don't know, 0.10. Okay. All right. Little box. And there's our string. And as I said, I'm going to pull was keep it at the 50 newtons. So then my applied force on this little train of boxes is going to be 50 newtons. Now, there are several ways to analyze this type of problem where we have multiple objects, okay? These ones are connected by a string, but they could also be in contact. And so the most general one is we're going to analyze each individual object, and it will generate a system of equations that we can then do a substitution in order to solve for all of the pieces, okay? So that one always works. There are other techniques, but I think we're going to just make sure we learn the one. We don't have a lot of time, so we'll just learn the one that always works. So that's the reason for doing this one. And so I'm going to label this one as box 1, and this one is the little box 2. Okay. And so we're going to go and we're going to identify all the forces on box 1. Okay. And so our first force should be our, well, let's start off with gravity. Okay. So this is mass 1 times g. So this will just be our, 98 newtons, so 10 times 9.8, just like it has been. And then we have the next force we would probably want to do would be our contact forces. Of course, the top one on the list of the contact forces was the normal force. So the normal force will be perpendicular to the surface of contact, and starting at the surface of contact, you will go through the object of interest. So this will be our normal force. Okay. And then we'll have friction. Now, the giveaway is that they gave us a coefficient of friction, so that explicitly tells us we will have friction. A lot of times they'll say, oh, the surface is smooth or something like that, or they'll put it on ice so that then there is no friction or whatnot. But this one, they gave us a coefficient. We definitely have it. Once again, once the, the train of boxes goes ahead and moves, then it's going to head, to the right. Shocking, I know. And so therefore, the kinetic friction force will be parallel to the surface of contact, opposite the relative motion. So since the box is heading to the right, then the kinetic friction will go to the left. Okay. So with gravity, normal, friction. We have my applied force here because I pulled on the lead box. And then we're also going to have the tension in the rope or the cord or whatever that was. Okay. So now the rule for the tension is that it's going to go, along the rope, but away from the object. And this is because you can only pull with a rope. You can't push. All right. So this will be starting at the object. We're going to go along the rope like this. The force of tension, like so. Okay. Now we can try to make sure that we have all of the forces acting on box one. Okay. And what we would talk about is that the only non-contact force is gravity. Everything else comes from thing touching box one, which was the table, which made the normal and the friction, me pulling, and then the rope. Since there is no other objects in contact with the box, there can't be any other forces. Now we should also go in and indicate the acceleration of our box. And so I would go in and say that the box is going to accelerate to the right, horizontally along the table. Okay. All right. Now let's move on to box two. So we should start off with gravity, I guess. So we'll have our gravitational force. So from the center of box two to the center of the earth, or locally it would go down. So this was 5 kilograms times 9.8. This will be, 49 newtons, like so. Okay. And then, in addition, it's in contact with the table. So there's going to be a normal force due to the surface of contact. The normal force will be perpendicular to the surface of contact. And starting at the surface of contact, it's going to go, through the object of interest, which in this case is up. This. Okay. And since we have a coefficient of kinetic friction, since the box is sliding to the right, the friction will go to the left, again, parallel to the surface of contact. Okay. And then we're going to have the rope. The rope will create a tension. Tension force will go along the rope away from the object. So that's to the right. Now, should there be an applied force on the box? Yes or no? What do you think? We got to know. We got to know. Those are correct. Why? That's right. Grab box one only and pulled. I didn't grab both boxes and pull. So the applied force is only attached to box one. So then these are all the forces, because the only thing touching box two is the rope and the table. Normal and the friction, tension there, gravity is the non-contact. Let's go in and put in our acceleration. And then, of course, one of the things that we're going to notice here is that, our notation isn't that great because I have multiple things labeled the same, right? I got gravity and gravity. And so to differentiate, we're going to do like the same thing that we did with the car and the motorcycle. We'll go ahead and do that. This is gravity 1. This is kinetic friction 1. This is tension 1. This is normal 1. This is acceleration 1. and then this is gravity 2, this is tension 2, normal 2, kinetic friction 2. I forgot my A on the acceleration, but it is A2, like so. Okay. And now at this stage, what's going to happen is we have an issue. Okay. So I need to talk about the issue we have and how we are going to resolve this. Okay. And the resolution is always the same, but it's in most of the books, they never talk about it at all. So again, it's one of those, where were you supposed to learn this thing kind of idea. Okay. I think our book actually mentions it a little. I think it has the most I've ever seen in any physics books on how we get by this. Okay. So number one, what we're going to do is we're going to count the number of unknowns. Okay. So we have the acceleration, the normal, the kinetic friction, the tension. So that's 4 unknowns on box 1. And then I have the acceleration 2, normal 2, tension 2, kinetic friction 2. That's 4 unknowns on box 2. So there are 8 unknowns. Okay. When we do the Newton's second law in each direction for each object and our friction, it's just like this. We're going to get, this is the number of equations we're going to get. We're going to get the Newton's second law in the y, we're going to get Newton's second law in the x, and we're going to get this kinetic friction force. There are 3 equations for each box. So 3 here, that is 6. We've got 8 unknowns. Okay. So I'm going to come back to here. So hold off on that for just a moment. Now what we're going to do is I'm going to have a little, I'm going to call it an aside. Okay. And so what we have going on is we have 8 unknowns. But we have only 6 equations. So if y'all remember from algebra class, in order to solve for 8 unknowns, we're going to need how many equations? Solve for 8 unknowns, we need 8 equations, 8 linearly independent equations. You get picky about it. We only got 6. So what are we going to do? So, how are we going to solve this? Okay. Now, all the problems that are presented are meant to be solvable. So you shouldn't get to the point where you go, yeah, well, we can't get the answers. That's the actual answers. I can't get the answers. No, that's not how it goes. Okay. So what happens is we make the following assumptions, and the assumptions are about this string. Okay. And basically, primarily what we're going to do is we're going to assume that it is an ideal string. Okay. And so what that implies is first off, that the string is inextensible. The string does not stretch. Okay. Inextensible. So what's the implication there? Well, let's look at this. If the string were to stretch, then when I pulled on box 1, it would move through a greater distance than box 2 in the same time. And so therefore we go from rest to different velocities in the same time. And so therefore we would have different accelerations on each box. However, if the string doesn't stretch, then each box moves through the exact same distance in the same time. So you go from rest to the same velocity. And in that same time, that means you get the same acceleration. So what we'll end up with is that the magnitude of the acceleration 1 is the magnitude of acceleration 2. So with the string, if the string does not stretch, then A1 is A2 is just A. Okay. So now we're down to 7 unknowns. And I'm going to come in, I'm going to wipe out the 1 and the 2 on these because they're just A. Okay. There we go. The second characteristic about our ideal string is that we will state that the string's going to be massless. Or if that bothers you, we can say that it has negligible mass. The mass of the string is negligible compared to the mass of the boxes, kind of things. Okay. And you're like, okay, so what does that do for us? Well, if I draw in my little string, there's the string in between the boxes. And what we have is that the string's going to accelerate with the boxes. And if we look at the forces on the string, then this will be our force of tension 1 would be to the right. And this is our force of tension 2 would be to the left. And then if I were to go in and pick that, to the right is the positive x direction, and we write down Newton's second law, then what we would get that the net force in the x is equal to m times ax. We would get that this would be plus force tension 1 minus force tension 2 is equal to m times plus a. So if there is a mass, then tension 1 has to be greater than tension 2. But if we can neglect the mass, we say this is negligible or that it's 0, then the implication is that the magnitude of tension 1 equals the magnitude of tension 2. We just call it Ft. Now we got 6 unknowns, and we have 6 equations. So we are now good to go. So let me get rid of the 1 and the 2 on those, and we shall proceed. Okay. So whoop, those go away. And now I'm going to go in and pick out our coordinate system. It'll be okay if we use the same for both, because really they look about the same. Since the accelerations are horizontal and to the right, I'm going to make horizontal to the right the positive x direction, and I'll make vertically up the positive y direction. And so then let's go in and take a look at each of the boxes. Okay. And so I guess let me write down for our box 2. We're going to do the sum of the forces in the y is how I usually like to start. Is equal to mass 2 times AY. And in this case, I'll have plus the force normal 2 minus the force of gravity 2, and that's it in the vertical, equals, and since the A is purely horizontal, then the Y component of A is 0. So we get that the magnitude of the normal is equal to the magnitude of the gravity, which is equal to our 49 newtons. This will allow me to solve for the friction. Friction kinetic 2 is going to be mu kinetic 2 times the magnitude of the normal force for 2. So that's 0.10 times 49 gives us 4.9 newtons. Okay. Then we can go in the x direction. The net force in the x is mass 2 times the x component of the acceleration. So I have this tension here, plus the force of tension, minus this friction kinetic 2. It's mass 2, and the A is to the right, which is positive. Okay. Don't know the tension. Kinetic friction was the 4.9. The mass of box 2 was 5 times A. Now this has two unknowns in it. So what we're going to do is we're just going to keep moving on. I'm going to move to box 1 and see what we can write down there. So when we come over here to, box 1, then I can write down my sum of the forces in the y direction is equal to mass 1 times AY. I will get plus force normal 1 minus force gravity 1. And since the A is purely horizontal, the y component is 0. Magnitude of normal 1 is magnitude of gravity 1 is our 98 newtons. This magnitude will tell us the friction. Friction kinetic 2 is UK2, magnitude of the normal 2. This is going to be 0.15 times 98. This gives me thank you, 14.7. There we go. Now we're going to go to the x direction. In the x direction, I've got the applied force minus the tension minus the friction equals my 10 kilogram box. Oh, I'm just going to call it M1 plus A, and I'll put the number in the next line. Sorry, forgot where I was. M1 times plus A. We know the applied is the 50 newtons. Don't know the tension magnitude. Supposed to solve Newton's second law for that. The kinetic friction is our 14.7 equals 10 times A. What you'll notice is that this equation also has two unknowns, and it's the same two unknowns that we had on the other one by the assumptions about the string, that the A magnitudes were the same and the tension magnitudes were the same. Okay. And so now what we can do is we have two equations, two unknowns, and we can solve. You may use any technique that you would like. So this is going to be minus 4.9 equals 5A. Let's collect this. So 50 minus 14.7 is 35.3. So 35.3. 3 and 7 is 1, 9, 10, carry 1, 3, 4, 5. Yeah, I think so. Okay. Now, as a graduate of college algebra, you should know a plethora of techniques to solve a system of two linear equations. You should be able to do, substitution, elimination, Gauss reduction, Gauss-Jordan reduction. You should be able to make augmented matrices out of them, put it into row-reduced echelon form, or for all I care, you could bust out Cramer's rule. I'm going to do substitution. If we get crazy, I might bust out an elimination. But we're going to stick to those. I think most people are pretty good with those. So I'm going to start here and move that 4.9, and then I'll solve for the force of tension. So then our force of tension is 5a plus 4.9. And then what I'm going to do is I'm going to take that and I'm going to substitute it into the other equation. Do not put it back into the equation you got it out of. If you do, you'll get something like 5a equals 5a, which, while true, doesn't tell you what a is. And so it's not useful. Okay, so just be a little careful here. We're going to plug it into here. And what I'll get is our 35.3 minus, and then that is 5a plus 4.9 equals 10a. And now what we need to do is I need to distribute this minus sign to both of the terms. Don't forget that second term with the minus sign. 35.3 minus 5a minus 4.9 equals 10a. I'm going to collect like terms. I'm going to move the 5a to the other side. 5a plus 10a is 15a. 35.3 minus 4.9. 13, that's 4 and 30, right? Thank you. And then to solve for a, divide both sides by 15. So then a is 2.03. Thank you. All right, now we got a. And so now what we're going to do is going to take the a and put it back into this formula to get the tension magnitude. So then our magnitude of the tension is 5 times our 2.03 plus 4.9. 15 point something? Yeah, 15.05. And there we have it. These were magnitudes of vectors. They came out positive. Directions look good. And so now we need to have just a brief discussion about what we're looking at. So now, one of the things that I allowed you to believe was that the signs on the solutions told you the directions. And in some sense, they do. But really what they tell you is whether you coded the direction correctly or whether the direction should go the other way. That's really what it tells you. It doesn't tell you if it's, right or left, up or down in the coordinate system. It tells you if you coded it in the correct direction or whether it should go the other way. Okay, so A being positive says we coded the directions for the accelerations in the correct direction. And here I picked that it went to the right, and here I picked that it went to the right, so it goes to the right and to the right. And then this tension magnitude being positive says I coded the directions on the tensions correctly. And so on box 1, I said it went to the left, but on box 2, I said it went to the right. And so those are correct. And so this is why you can't interpret this direction at this being positive negative as the direction, because it's not like both tensions went right. One went right, one went left. Both accelerations went to the right, but the tensions were one's right, one's left. And those are correct. So by getting a positive answer, the directions we coded in the vectors, which is why I made such a big stink about doing your directions first, that those were correct. Okay. Are those third law pairs? What do y'all think? Yay or nay? This is 15.05 newtons to the left. This is 15.05 newtons to the right. Are those third law pairs? have several yeses. We did have it pointed out that they are indeed the same type of force. But there's an issue with the on and the by. This tension is on box 1 by the rope. This tension is on box 2 by the rope. The on and the by don't trade. So this makes them like, I don't know, cousins or something like that. It's close, but not quite right. Okay. The third law pairs to those forces are here on the rope. This FT1 is the third law pair to that one. This is the tension on box 1 by the rope. This is the force on the rope by box 1. It's here. And then this is the third law pair to that one.